Engineering is often about finding a compromise solution between competing goals. You may want your design to have the lowest possible cost, while the peripherals that you need may drive the cost up. In Section 7, you'll see how to use software to create a UART on a device that may lack that peripheral. The LaunchPad board doesn't have a dedicated UART connection. Instead, the UART connections on the LaunchPad board are routed to the emulator's USB connection. Since this USB connection is part of a composite port, your laptop can recognize the UART as a virtual COM port. You can use the terminal program running on your laptop to connect to and transfer data across this serial connection. A simplified view of the USCI, or Universal Serial Communication Interface, is shown on this slide. The USCI is split up, or rather offers you UART, SPI, and I2C, and it's split up into two sections. The A portion of this offers you 3 or 4 wire SPI connectivity, either slave or master. It offers you UART connections, and it offers you IRDA if you're doing infrared. The B0 portion of this also supports SPI, 3 or 4 wire, and in addition it supports I2C. The protocols offered on the USCI are SPI, I2C, and UART. SPI is the serial peripheral interface. The intent with this is to offer you a simple way of connecting up a SPI master to a SPI slave. Now, the master doesn't have to be the microcontroller. It can be an ADC, and often you might have it be the ADC or a timer where you want that to be able to wake up the processor. There's only 4 connections in that, the S clock and the rest of the signals that you see there. I2C is the integrated circuit interface. The point with this is to offer you a way of connecting to multiple slaves. For instance, if you have multiple DACs, multiple ADCs, and you might be able to talk to another microcontroller over this. So you have a whole series of these. So a single master and multiple slaves here. UART is your typical universal asynchronous receiver transmitter, a serial way in which the serial clock and data is combined on those lines. This is a full duplex implementation so that you can talk either one of these. Either side can be a receiver and either side can be a transmitter. Again, your selected device may not have a hardware UART on board, so we'd like to take a look at doing a software UART implementation. A simple software UART implementation using the capture and compare registers of the timer to emulate the UART communication is possible. It's a half duplex and it's a relatively low baud rate. 9600 is the recommended limit, but we usually use it around 2400. The bit timing, how many clock ticks one baud is calculated based on the timer clock and the baud rate. One of the capture and compare registers is set up to transmit in the timer compare mode, toggling based on whether the corresponding bit that's coming in from the software is a 0 or 1. The other capture and compare register is set up as the receive in the timer capture mode with a similar principle. The functions are set up to do transmit or receive a single byte, 8 bits, appended by the start and the stop bits. As you can see below, there's a application note, SLAA 078. Take a look at that if you want additional information. But the lab that we're going to do here will show you not only how to implement a software UART, but also how to go in and take some of the code examples that are written for the MSP430 and use them, cut and paste, and use them effectively in your design and your code. The COM port communication on the LaunchPad board is set up in basically 2 ways. If you're doing a software UART, the pins that you talk out of are connected to the emulation port that will end up the USB interface. You could connect directly to those pins and use those as your as your UART connections. And if you take a look down on the board, you can see that port 1 pin 1 and port 1 pin 2 are both connected as the UART. Now, if you're dealing with a part like the 2553 that has a hardware UART on board, those UART pins are directly connected to the peripheral UART inside the device and work in a similar fashion. Now, like I said, the UART is connected to the emulator. The emulator sends that information via a virtual COM port back to the PC. The emulation hardware implements a composite driver that you may have already noticed. The board in. You may have seen it as that's recognized by Windows. And once again, the UART transmit and receive pins match the EZ430 or SPI-by-wire JTAG interface pins. So you can see that it comes, if you take a look at the circuit diagram or schematic for the LaunchPad board, you'll see that those UART pins and the UART connections come directly up into the emulator, and then we can transmit information directly up to the PC. Your implementation, you would not have the emulator, you would not have the capability to do that, so you would come directly out a serial port instead. Texas Instruments provides a substantial selection of C and assembly example code for all of the peripherals on the MSP430. Lab 7 will demonstrate how to easily use this sample code to add UART capability to your code on a device that may lack this hardware peripheral. Let's create a new project by clicking File, New, CCS Project. Go ahead and make the selections shown below. Lab 7, make sure your project's in the Lab 7 folder, and that you select the appropriate part, whether it's the 2553 or the 2231. At the bottom, make sure you pick Empty Project, and when you're done, click Finish. In this lab exercise, we're going to be building a program that transmits the ASCII characters HI, high, or low, or in, using the software UART code. On the 2231, the 2231 does not have a hardware UART on it. The 2553 does have a hardware UART on it. But in either case, it'd be more interesting to use the software UART code just to show you the way that we are able to take example code, easily drop it into our system, and build a new set of software. So this data will be communicated, the high, the low, or in, will be communicated through the USB COM port and then onto the PC for display on a terminal program. The UART code utilizes timer A2, so we'll need to remove the dependence on that resource from our starting code. Then we'll add some trip point code that will light the red or green LED, indicating whether the temperature is above or below or inside some set temperature. Then we'll add the UART code and send messages to the PC. The code file from the last lab exercise will be used as a starting point for this lab exercise. So in the first step here, open up lab6a.txt using file open file out of the lab 6 files. Go ahead and copy all of the code from lab6a.txt and paste it in the main.c, erasing the previous contents. This will be the starting point for this lab exercise. You should notice this is not the low power optimized code that we created in the last part of the lab 6 exercise. The software UART implementation requires timer A2, so using the fully optimized code from lab 6 wouldn't be possible. But we can make a few adjustments and still maintain fairly low power. Go ahead and close the lab6a.txt file, and if you're using the 2231, make sure you make the appropriate change to the header file at the top of main.c. As a test, build, load, and run the code. Go ahead and remove temp raw from the expression pane. If everything's working correctly, the green LED should blink once every 3 seconds, but the blink duration should be very, very short. The code should function exactly the same as it did in the previous lab exercise. When you're done, halt the code and click the Terminate button to return to the editing perspective. In step 4, we need to remove the previous code's dependence on timer A2. we can use the watchdog timer as an interval timer rather than a watchdog timer. So change the config WDT function so it looks like what's shown below, that we are going to do a WDT control. We're going to say WDT under ADLY 250. That sets the watchdog timer interval to something less than a second. And then enable the watchdog timer interrupt. The selection of intervals for the WDT Plus is a bit limited, but the WDT under second delay running on the VLO. Those bits set the following. They set the watchdog timer password, they select the interval timer mode, they clear the count value, and they put they set up the watchdog timer clock source select to the one that we're interested in. In step 5, the code in the timer A0 ISR now needs to run when the watchdog timer triggers. So change the top portion up there from timer A0, timer 0 A0 vector, timer A, to watchdog timer vector WTT at the top, as shown in the steps in the book. In step 6, there's no need to handle the capture compare register in the watchdog timer ISR, so go ahead and delete the CCR 0 plus equals 36,000 line. In step 7, there's no need to set up the timer A2 now. Delete all the code inside config timer A2. Go ahead and build, load, and run the code. Okay, so we're looking at the light blinking, and the light's blinking about once a second there. Very nice. Once you see that, go ahead and click the Terminate button and return to the editing perspective. If you need to, this code can be found in the lab7a.txt file in the Files folder. So now we want to go ahead and add the UART code. In step 9, delete both P1 out lines of code in the watchdog timer ISR. We're going to need both LEDs for a different function in the following steps. In step 10, we need to change the transmit and receive pins. That's port 1, pin 1, and port 1, pin 2. If you're looking at the board, you can see those labeled on the silk screen on the MSP430 from GPIO to the timer A0 function. Add the first line as shown below in the workbook to your config pins function, and then change the second line as shown. In step 11, we're going to need a function that handles the transmit software. Adding a lot of code tends to be fairly error-prone, so we're going to add the following function by copying and pasting it from here, or you could copy and paste it from transmit.txt in the Files folder to the end of main.c. So this function transmit the character from tx byte. So the value in the variable tx byte will be transmitted out through the transmit pin on the MSP430. Once you've pasted in that entire function, you need to make sure you put a function declaration at the beginning of main.c. That's a void, transmit, void, semicolon. In hang on, we're making sure that we've got it right. In step 12, the transmission of the serial data occurs with the help of timer A2. It sets all the timing that will give us a 2400 baud data rate. Cut and paste the code below, or copy the contents of timer under A2 ISR.txt and paste it to the very end of main.c. So this is going to go off when the timer goes off and will help handle the transmission. Step 13. Now we need to configure timer A2. Enter the next two lines into the config timer A2 function in main. So it looks like this. cctl0 equals out, and then there's a timer A control tassel 2, mode 2, ID 3. So this is SM clock over 8 in continuous mode. So to make all that code work, we need to add some definitions to the top of main.c. We need to do a pound define of txd to bit 1, a pound define of the rxd to bit 2. We're going to define the bit time as 13 times 4, so that's a 0d. We need to add a declaration for an unsigned integer of tx byte and an unsigned character of bit count. So we've added a lot of code. Let's do a test build without doing a debug. In the Project Explorer pane, right-click on Main and select Build Selected Files. Check for any syntax errors in the console and problems panes. We're good. Now go ahead and add the following declarations to the top of main.c. We need we're going to go in here and do our temperature readings and have our temperature set. So we're going to add a volatile long temp set equals 0. So we'll do a set on this, and a volatile int I to the very top. The temp set variable is going to hold the first temperature reading made by the ADC10. We'll then compare future readings against that to determine if the new measured temperature is either hotter or cooler than that value. So note we're starting out with the variable at 0. That way we can use its non-zero value after it's been set to make sure we only set it once. We'll need the I in the next piece of code down here. So in step 17, add the following control code to the while loop right after the line containing bis SR register LPM 3 bits plus GIE. This code is available in the while.txt file if you want to use it from there. So this is code that I wrote rather than pulling it directly from the code, the existing code examples. What this code does, no, we're still getting it in place. What this code does is it sets 3 states for the measured temperature, low, high, and in, that are indicated by the state of the green and red LEDs. It also sends the correct ASCII sequence to the transmit function. So you can see we're using a preset of 5 degrees plus. If it's greater than 5 plus, or if it's less than 5 low, right, we're going to test for low, for high, or if they're both done, we're going to set for a 2 degree that's in range. So we'll be able to get all 3 of those situations, and that's what we're going to send over the USB port through the UART. So in step 18, the ASCII equivalents that are going to be transmitted to the PC are for low, it's LO, line feed, backspace, backspace. So that's, you can see the hex sequence that's right there. And then for high, we're going to send that HI, and then line feed, backspace, backspace. This is mostly for formatting. And then again for in. The terminal program on the PC is going to interpret that ASCII code and display the desired characters. The extra line feeds and those backspaces format it the way that, so it'll look real pretty on there. So we need to add those arrays to the top of main.c so that those transmit elements are exactly what we hope to transmit. In step 19, we need to change the clock settings for the basic clock control register 2 from SELM selection 0, divm 3, and divs 3. We need to just go ahead and change all those to 0. So make that change in your config clocks function. In the next step, build and load the code. If you're having problems, compare your code with lab7finish.txt found in the files folder. Don't take the easy route and copy paste the code. Figure out the problem. The process will pay off for you later on. Believe me, none of our code runs right the first time. In step 21, next we need to find out what COM port your LaunchPad is connected to. This should be the same as earlier. In Windows, click Start, Run, and enter devmanagement.msc in the dialog box, and then click OK. If you're running Windows 7, you can type Device Manager into the search window at the bottom. Click the symbol next to ports and find the port named MSP430 Application UART. Go ahead and write the COM port number down in the workbook here. We got 22. Go ahead and close the Device Manager. Make sure your code's running. Minimize Code Composer, and run Hyperterminal if you're running Windows XP. If you're running Windows 7, you need to use TerraTerm or your other favorite terminal program since they removed Hyperterminal. In Hyperterminal, give the new connection a name and click OK. In the next dialog, select the COM port you found in the previous lab step in the Connect Using box. Click OK. So in your terminal display, you'll likely see in, as we see here, displayed over and over again. So we're going to exercise the code. We're going to reach over here and warm up the device. I'll put my finger on the top of the device. And at some point it should say hi. I may have a hard time getting it to cool down, and you'll also notice that the red LED is on. If we can get the device to cool down, it will say low. In the middle, both LEDs are off, so now we're back to in. We're right at the edge there where it's going between one and the next. It may be hard to get it to cool down. Remember, the reference temperature was taken when the code was first run. This would also be a good time to note the size of the code that we've generated. In the console pane at the bottom of the screen, note that you see MSP430, program loaded, code size, the text is shown at the bottom. Based on what we've done so far, you could create a program more than 20 times this size and still fit it comfortably inside the 2553 memory. When you're done, go ahead and close the terminal program. In step 24, terminate the active debug session using the terminate button. This will close the debugger and return CCS to the edit view. In step 25, go ahead and close the Lab 7 project in the Project Explorer pane. You're done.